So today we're going to talk about average acceleration. And to do that, I want to look at a table of values that shows the time and the position, because we could find the average velocity from this, okay? Because the change in time each time is 1 second. And I did this to make some numbers just to make it really easy for us to see, okay? So from 0 seconds to 1 seconds, our position went from 5 to 6. So that's an increase of one meter in 1 second. So my slope, okay, or my change in position over change in time, or my average velocity in that interval would be 1 meter per second, okay? And then from 1 second to 2 seconds, we went from 6 to 9. So that's 3 meters per second. And then from 9 to 14, or I should say from 2 to 3 seconds, we went from 9 to 14. So that's an increase of 5 meters per second. And then what happens here is between 3 and 4, we went up 7 meters per second. And from 4 to 5, we went up 9 meters per second. You might be seeing a pattern here. And then from 5 to 6 seconds, we went from 30 to 41. That's an increase of 11 meters per second. And from 6 to 7, that was an increase of 13 meters per second. And from 7 to 8, we went from 54 to 69. That's an increase of 15 meters per second. Okay. And then from 69 to 86, that's an increase of 17. In 1 second, we increased it by 17 meters per second. And then from 9 to 10, we went from 86 to 105. That's an increase of 19 meters per second. Okay, so if you look at this, okay, as time marched on, right, as time went by, look what happened to our average velocities. They were increasing, right? And they were increasing, okay, at a constant rate. So the velocities were increasing each second. So if you look, this is called the second differences in mathematics, okay? But if you look at this and these two, okay, then we could say also, like in 1 second, we went from 1 meters per second to 3 meters per second. So that would be 2 meters per second. And then 3 to 5, 2 meters per second. From 5 to, in one, roughly, to help you explain this, in 1 second, we went from 5 meters per second to 7 meters per second. So that is 2 meters per second. So that means every second it's increasing, the velocity is increasing 2 meters per second. So that's an increase of 2 meters per second. And this is an increase of 2 meters per second, and so on, right? And if you look, all of these were going up by 2 each time. That right there, when the velocities are increasing and they're increasing at a constant rate like this is, okay, we say that, well, even anytime, I should say this, anytime the velocities are increasing like this, or changing, we call that acceleration. All right. Now, in this physics class, these have to be the same. All right. So when you get your acceleration, it's always going to be constant. It has to be. Because if the acceleration was changing, we actually need calculus for that. Okay. So we can't do it because you guys don't know calculus. All right. So we actually need calculus to do that if we're changing accelerations. Okay. So everything we do in this class, the accelerations are not going to be changing. They're going to stay constant. Okay. So this is basically, we're seeing here, we have positive acceleration. And it's a different unit. I'm going to go in more on that later. It's meters per second. Okay. So meters per second. So it adds, what acceleration does, a positive acceleration adds velocity to an existing velocity. So like this is adding 2 meters per second. Every second it adds 2 more meters per second. okay? All right, so let's take a look at one more different situation. We're going to take a look at this on the graph in just a little bit, okay? But let's look at another table. Okay, so if you look at this one, all right, a little bit different. This is going to be a little bit different situation, okay? At 0 seconds, we're going to start at 8 meters, and then 1 second later, big huge jump, right? 27 meters. So in 1 second, that increased 19 meters in 1 second. So that'd be 19 meters per second. That'd be the average velocity on that interval. On this next interval, okay, we went from 27 to 44. That's still an increase, right? But this time it's only 17 meters per second. And then the next one is from 44 to 59 in 1 second. So that's an increase of 15 meters per second. And then from 3 to 4 seconds, we went from 59 to 72. That's an increase of 13 meters per second. And then from 4 to 5, we went from 72 meters to 83 meters. So that would mean we went up 11 meters per second. And then 83 to 92, that means we went up 9 meters per second. 92 to 99, that would be 7 meters per second. 99 to 104, that'd be 5 meters per second. 104 to 107, that would be 3 meters per second. And 107 to 108, okay, that would be 1 meter per second. So if you look at the velocities this time, yeah, they're all positive, right? All the velocities here are positive, but they're actually decreasing. So when the velocities are increasing, all right, when the velocities are increasing, we say it has positive acceleration. And when the velocities are decreasing, we would say that it would have negative acceleration. Because if you look at this, we're now going -2 meters per second per second. And every time we're going down 2 meters per second per second, -2 meters per second per second. So each second we're going down 2 meters per second. That's what that means. Meters per second per second. Okay, so we keep going down -2 meters per second per second. So we would say this one has negative acceleration. Now that's not decelerating, okay? Decelerating is actually slowing down, okay? Sometimes when you have negative acceleration, you could be slowing down, but not always, okay? And I'll explain that. That's actually a future lesson, okay? So negative acceleration. Okay, and I should say this, velocity is decreasing. Okay, and here, positive acceleration, because the velocity is increasing. Okay, so that means what we're doing right here is actually we're finding the slopes of velocity, right? And that's actually what average acceleration is. So let me turn the page, and did you guys get, just realized you guys didn't see that. Okay, so up here, positive acceleration, what I wrote was velocity is increasing, and down here, negative acceleration is when velocity is decreasing. All right, sorry about that. Okay, let's go to the next page. Okay, so A bar, or the average acceleration over an interval, is the change in velocity over the change in time. So V sub f for final velocity minus V sub I for initial velocity over T sub f final time minus T sub I. Now, when T sub I is 0, when the initial time is 0, then this T sub f would just be how long it went, okay? All right, so a couple things. This is different. We've been looking at line graphs a lot. All of a sudden, it's starting to curve, right? And if this is curving, okay, we can tell because the position is increasing, we can tell that the velocity is positive. So that's one thing we can tell from this, okay? Velocity is positive because the position is increasing. So if position is increasing, then we would say that the velocity has to be positive, because if we go along, go through a time interval, we're getting a bigger position, right? We're going up, okay? Now, here's something else. I can tell from this graph, and I'm going to want you to be able to do this, is because this is bending up, all right? And I'm going to show you one little quick thing. I'm trying to get a ruler. What causes bending in a curve, okay? And this is basically is what it is, okay? If you look at like the slope at one point, it's called the tangent slope, okay? Right there, that slope right there is gonna be less than the slope way up here. Okay, so what you're seeing here is that the slope is increasing, right? Which means the velocity has to be increasing. So that means if our velocity is increasing, that would mean this is showing positive acceleration, okay? So we would say the acceleration is positive. In mathematics, we call it concavity, all right? But here we're just gonna say bending, it's bending up, it's cupping up, okay? And we know it has the acceleration is positive because it's bending up, okay? Whenever you see a curve bending up, it's gonna have positive acceleration, okay? If you see it curving down, which we're gonna see in just a minute, that would mean it has, the acceleration would be negative, okay? So right here, okay, when this happens in a certain way, which has to happen in our class, okay, because we're taking algebra-based physics, there's a calculus-based physics too, okay? But what happens is the velocity has to come out to be a straight line, okay? For our class, this has to happen. So if we have positive acceleration, this has to be constant, which actually causes the velocity to be a line, but it's no longer a straight line. Like last week, we were drawing horizontal lines for velocity, right? Now they're still going to be lines. They still have to be lines, but they can be diagonal lines now, okay? And you're going to get these diagonal lines when you have some type of acceleration, okay? So this isn't a technical thing, but velocity is a diagonal line, slanted line. Probably slanted. You know, I like slanted better. Slanted line when there is acceleration. Okay, and because that's a line, if we find the slope of this, then that's going to give us an acceleration. So this is kind of like what we were doing with position velocity last time, right? We had a velocity that was nice, or a position that was nice line graph, and then we were able to find the slope, which is velocity, which would be a horizontal line. Okay, and that's what this is going to be too. Okay, we have to, all of our accelerations in this class are going to have to be horizontal lines, or no acceleration at all, which is still a horizontal line. It would just be right here. What we were dealing with last week was all the accelerations were zero, okay? And that's why this line, these were horizontal, okay? But when you have an acceleration, that's causing this position graph back up here to be curving, right? Okay. All right, let's go to the next page. All right, so now if you look at the slope right here, right at a point like right here, where right where it's touching at one spot, okay? Compare that slope. That's pretty big. It's positive, but it's pretty steep, right? Compared to the slope over here, that's still a positive slope, but it's not as steep as this one. So this has a greater slope, which means the slopes have to be decreasing, okay? So, and if you look, this curve, it's bending down now, right? So again, because the position is increasing, all right, I know the velocity is positive. If it was decreasing, then the velocity would be negative. And you can still have velocity that's negative and still have the bending, okay? So we see this bending here, right? And because it's bending down, and what's causing that is this slope is really high, and this slope is still positive, but it's not as large as this one, right? So what's happening is the velocities are decreasing now, and that's going to happen when the acceleration is negative. So we know from this, I should say this, whoops, velocity is positive because the position function is increasing. Position is increasing. And we know the acceleration is negative because it's, lack of a better term, bending down. Bending downward, bending down. Or some people say cupping down. The mathematical term is, again, concavity. It's concave down. That's what we would say. Bending down is good for physics, okay? All right, so the velocity is still positive. So let's take a look at this. Okay, so because these velocities are all positive, that's why it's all above the x-axis here, or the time axis. The velocities are all positive, but this is decreasing, right? So the slope of here is a negative value, and it turns out to be -2, and that's what comes up right here. So this is showing we have a negative acceleration, okay? This is the position graph, this is the velocity graph, and this is the acceleration graph for all of the same motion, okay? And I showed you that earlier today in the preview, okay? All right, so velocity, again, velocity is a slanted line. When there is a constant, I should say this, when there's a constant acceleration. Okay, so you're gonna see this also, okay? We call this, the acceleration is constant. We could also say uniform acceleration, okay? Constant acceleration. And that's the same as uniform acceleration. So we got to learn to read a little bit too. So uniform acceleration, constant acceleration, same thing, okay? It just means the acceleration is not changing, okay? All right, so again, last week we looked at, we had no acceleration. So we had velocity, but we didn't have any acceleration, okay? So when the velocity function is constant, right, that would mean that there's no acceleration, there's zero acceleration. And that's what was happening last week. Okay, let's do some problems. So here's the first problem, okay? A car is traveling at 25.2 meters per second, speeds up to 27.8 meters per second in 2.3 seconds. What is the car's average acceleration? Okay, so we know that the average acceleration is the change in velocity, okay? So it's traveling at 25.2 meters per second and speeds up to this. So this one right here is my V sub I. It's the initial one. I'm starting there and I'm going to speed up to this. So that's my final velocity, okay? And I know I do this in 2.3 seconds. So that's my delta T. So I know V sub I is this 25.2 meters per second. You want to get in the habit of writing this stuff down like a column of everything you know, okay? Because these problems are going to, in the next week or so, they're going to get harder and harder and harder, okay? So then V sub I is this, and then V sub F, which is the final velocity, we sped up to this, so 27.8 meters per second. And we know our delta T is equal to 2.3 seconds. And we're trying to find and you always want to write also what we're trying to find, which is the car's average acceleration. So A average equals, you could also write A bar. I'm going to go back and forth. So you can use which method you like to show average acceleration. It's going to be your choice. Okay. So I know that the average acceleration is equal to V sub F minus V sub I over delta T, or T sub F minus T sub I, okay? So in this case, V sub F is 27.8 meters per second minus 25.2 meters per second. And those are the same units, so I can subtract over 2.3 seconds. And this is also seconds. So you got to realize that if the time units or the distance units don't match, we're going to have to do a conversion, okay? All right, so 27.8 minus 25.2. All right, what would that give us? I'm grabbing a calculator even myself. I'm tired tonight. 27.8 minus 25.2, and you get 2.6. Okay, so this is 2.6 meters per second per 2.3 seconds. Okay, so I'm going to show you what happens with the units here, okay? It's very similar to what we did before, okay? So what happens here is I'm going to multiply this by seconds, or we could do 1 second. You can do seconds also, okay, or just 1 second. So this is a version of 1, but what happens is when we multiply this, we get 2.6 times 1, which is 2.6 meters. So this is the same as 2.6 meters over 2.3 second times second, which is seconds squared. All right, so what I'm trying to show you here is that the unit for acceleration is meters per second squared, okay? So that's gonna be our unit. That's our standard unit, meters per second squared. Okay, so now this has two significant figures, this has two significant figures, so our answer is gonna have two significant figures, okay? So 2.6 divided by 2.3 gives us 1.13, okay? So 1.130434783 meters per second squared. But what did I just say? We can only have two significant figures, right? So this is that 1 point, and then here's 1. This third significant figure, which is 3, is going to cause that 1 to stay 1. So this rounding to two significant figures would be 1.1 meters per second squared. And that's our answer. That was the average acceleration for these 2.3 seconds. Okay. All right. Let's do another problem. Okay, so for this next problem, a shuttle bus slows down with an average acceleration of negative 1.8 meters per second squared. Okay, so we know from the units that that has to be an acceleration. Okay, and it's a negative acceleration. How long does it take the bus to slow from 9 meters per second to a complete stop? So now we got to infer, what does this mean for a complete stop? Okay, we were starting at this 9 meters per second. So that is our v sub I. That's our initial velocity. That's the velocity we're starting at. So that's going to be 9.0 meters per second. For it to complete stop, that would mean our final velocity would have to be 0. Okay, so v sub f has to be 0.0 meters per second. My change in time, that's actually what I'm trying to find, right? How long does it take? So that's our question mark right there. And then a shuttle bus slows down with an average acceleration of, okay, so there's our average acceleration, right? Our A bar, our acceleration, excuse me, I can't say it. Average acceleration is negative 1.8 meters per second squared. Okay, once again, I know that the average acceleration is equal to the final velocity minus the initial velocity over the change in time. I could multiply both sides by delta t, and that would give me the average acceleration times delta t would be the same as the final velocity minus the initial velocity. Okay, so I can start putting some stuff in here because this is the one I'm trying to find, right? So this average acceleration I know is negative 1.8. So negative 1.8 meters per second squared. And then times my delta t is equal to my final velocity, which is 0.0 meters per second, minus my initial velocity, which is 9.0 meters per second. Okay, so that gives me negative 1.8 meters per second squared times delta t is equal to, and this is negative 9.0 meters per second. Okay, so what I'm going to do is I want to get this delta t by itself. Well, I'm multiplying by this. So to get this delta t by itself, I'm just going to divide both sides by negative 1.8. So my delta t is equal to negative 9.0 meters per second divided by negative 1.8 meters per second squared. Okay, now this time I need to get rid of this second squared. Okay, so I'm gonna, and multiplying by second squared will get rid of the second squared and it will also get rid of the seconds. So I'm gonna multiply by second squared over second squared. Okay, so when I multiply these, my seconds are gonna cancel and I'd be left with 1 second. So this is gonna wind up, my delta t is gonna wind up being negative 9.0 meter times seconds over, and then right here, my seconds squared and this second squared, so those are gonna cancel and I'm left with negative 1.8 meters. And then look what happens. My meters cancel and I'm left with negative 9.0 divided by negative 1.8. Now that's going to be a positive, and you should realize that delta t is always going to come out to be positive, okay? And we have two significant figures here, and we have two significant figures here, so our answer needs to have two significant figures, okay? So, and I'm fine, you know how on the previous problem I wrote all the decimals out? You don't have to do that, okay? So this is negative 9.0 divided by negative 1.8, and we just wind up with a nice clean number, right? It's 5. It actually, we need two significant figures, so this actually comes out to be 5.0 seconds. Okay, whoops. Sorry. So we wouldn't want to write it as just 5 seconds. We actually are more accurate than that, right? It's actually 5.0 seconds. Okay. All right. So that's how long it took to go from 9 meters per second to a complete stop. This is actually when an accident happens, they measure, well, it's a whole bunch of more math than that, but they actually measure the skid marks. And what they're doing is they're trying to figure out how long it took the person to stop. And then based on that, they can tell how fast you're driving and see if you're speeding or not. Okay. All right. Last example. So I wanted to throw this problem in here because we're going to have to do some converting of units. Okay. So, and we got to realize when we need to do this. Okay. So a car uniformly accelerates at 2.3 meters per second squared. Okay. So that's my average acceleration. Okay. That's my A. If the car's initial velocity was 23.4 meters per second, what is the car's final velocity after 2.3 minutes? And this is the kicker. This is what you should realize. Wait, this is all in seconds and this is in minutes. So I need to convert this to seconds. Okay, so let's do that. So 2.3 minutes and times, and we know 1 minute is exactly 60 seconds. Okay, so now this is 2.3 times 60. And we get 138. Now, I know we should only be using 2 significant figures, but we're going to need to use all of this. Otherwise, we create what's called rounding errors, okay? So we're going to use 138 seconds. We're going to use all of it, okay? Otherwise, we come out with rounding errors. Okay. So now we know what's everything that we know now. We know acceleration, the average acceleration is this 2.3 meters per second squared. The car's initial velocity is 23.4, so that's V sub I. V sub I is 23.4 meters per second. What is the car's final velocity? So that's actually what we're trying to find, V sub F, after 2.3 minutes. Okay, so now delta T is equal to 2.3 minutes, but we now know that is 138 seconds. Okay, so again, we know that the average acceleration is the final velocity minus the initial velocity over my change in time. So my average velocity, I can multiply both sides by this delta T, and I would have the average acceleration times my change in time is equal to V sub F minus V sub I. Okay, so let's just start putting everything in. So this is 2.3 meters per second squared. And my change in time is 138 seconds. And my final velocity is, that's what we're trying to find, V sub F. And then minus my initial velocity is 23.4 meters per second. Okay, so 2.3 times 138. And we get 317.4. And okay, so this second cancels with one of these. So we're left with meters per second is equal to the final velocity minus 23.4 meters per second. And then to get the final velocity, I'm just going to add 23.4 to both sides. So 317.4 plus the 23.4. And we get 340.8 meters per second. And that would be my final velocity. Okay, now, Yeah, so that'll be our final velocity, okay? And on a problem like this where you have multiplication and division, all and subtraction, addition, and all that, let's not worry about significant figures on this problem, okay? Let's just worry about when we're just strictly doing multiplication or division, okay? All right, so this is gonna be 340.8 meters per second for our final velocity.